Welcome everybody to the 75th anniversary celebrations here at NASA Ames Research Center. This is the last talk of 18 talks presented by the Office of the Chief Scientist. So NASA Ames Research Center has been pursuing some of humanity's grandest questions, both philosophically and scientifically, and thoroughly through a multidisciplinary and international perspective. Astrobiology is seen as kind of a cross-cutting discipline across most of what NASA science missions have done. And kind of in the spirit of astrobiology, there are three fundamental questions that generally are addressed. And it's, where did we come from? What's the evolution of life? Where is it evolving to? If we are alone, the search for life in the universe. And ultimately establishing where we're going next as an interplanetary species. The Kepler mission was launched in 2009 and has radically altered our view of planets, planetary systems, and ourselves, really. And approximately, I think, 1,500 planets have been discovered. And what's interesting about this is it really addresses this second question of, is there life in the universe? Are there habitable planets? Is there intelligent life in the universe? Dr. Jon M. Jenkins received his bachelor's degree in electrical engineering and applied math, Georgia Tech Institute of Technology, both his master's and PhD in electrical engineering from Georgia Tech. He currently serves as co-investigator for data processing for both the Kepler mission and the upcoming transiting exoplanet survey satellite known as TESS. Today's talk is entitled Chasing Shadow Worlds, Exoplanets from Kepler and Beyond. Please join me in welcoming Dr. Jon Jenkins.
Well, good afternoon. Thank you for coming to spend the afternoon with me. You might have thought the exoplanets got their start in 2009 when Kepler launched, and I wouldn't blame you if you thought that, but actually it started much earlier. But can any of you remember what life was like before exoplanets? And this is actually a picture of myself when 2 years into my tenure with the SETI Institute here at Ames. When I was thinking of alien worlds, but I was thinking mainly of Venus, I'd come here to continue my research into remote sensing of planetary atmospheres. At the time I was working on Pioneer Venus data, and Magellan was in orbit, and I was working on Magellan data. It was a fascinating, exciting time to be here because I'd gone to Georgia Tech. My advisor was the only professor doing space research on the campus, and suddenly I was here and surrounded by lots of planetary scientists, astronomers, geophysicists. It was an exciting time. But in October of 1994, both Pioneer Venus and Magellan crashed into the atmosphere of Venus, ending their sojourn. And so I was high and dry without a data source. I did indeed fall into bad company back circa 1988, 1989, when I was starting to work on the Pioneer Venus data, and I met Bill Barucki, who became the PI for Kepler, of course. But he was a co-investigator on Pioneer Venus studying lightning. So he and I go way back. In 1994, it was also a watershed moment for myself because another person, Lawrence Doyle, whom I met my first day on campus here, also worked for SETI Institute, became involved with an international coalition of astronomers who were interested in finding transiting planets around binary stars. And they'd picked the smallest known eclipsing binary at the time, CM Drac, to observe. And they needed somebody to come up with a detection algorithm. I'd go to lunch with these guys, and they would complain about how hard it was to come up with a detection algorithm, and I got interested. And it was a real puzzle. But we never got funding. We observed for 6 years. I did write detection algorithms. They worked. We put good upper limits on any planets that were there. But that work brought me to the attention of Bill Barucki later, who then asked me to join his team. Now, in 1994, here is a picture of all the known planets in the universe. Of course, there was one extra that we got rid of later. But dwarfs are people, so dwarf planets are planets too. At any rate, we thought that all the gas giants would be found in the outer part of the solar system when we were finding planets, because they have to form there. It's too hot, interior to about 5 AU, for water to exist and for you to get water and ice, that kind of thing. So we knew that giant planets had to exist in the outer part of the solar system, and that the rocky planets, ones that we can stand on, had to be closer to their star. And all the models that we'd come up with predicted that that would be the case. So one of the themes, I'll try to remember to say it more than once, is that it's very difficult to extrapolate from a sample of one. And you often get it wrong. Experts become fools quite quickly once they start to extrapolate. Now here's the picture we have today, or at least as of about 2 years ago. This is an XKCD cartoon. And it shows all 768 known planets at that time, drawn to scale. And if you look closely, you can find the solar system. You can see that most planets detected up to this point in time look nothing like the planets in our own solar system. Here's some help for you. Here's our solar system right here. You can see Jupiter is not the biggest bully on the block. There are a lot of planets that are much bigger than Jupiter. And indeed, the first planets we found were much bigger than Jupiter and much closer to their star than Jupiter is to ours. And there are a few small specks here that are comparable in size to Earth or thereabouts within a factor of 2. Those were Kepler discoveries, of course. Well, how does Kepler work? It's very simple. We look to watch for occasions when a star blinks at us as a planet crosses the face of the star. We don't image the star or resolve it. We measure the brightness as a function of time, looking for these dips in brightness corresponding to those times. The depth of the transit is the relative area of this planet to the star. If you block 1% of the light, then the planet's area is 1% of that of the disk of the star. It will repeat once per orbit, and so the interval of time between the two transits tells you the year. If you know the mass of the star, then that period, together with Kepler's laws, gives you the distance, the mean distance to the planet. That, together with the size and the effective temperature of the star, allow you to estimate that equilibrium temperature that the planet is experiencing, so that we can estimate the range of distances from a star for which liquid water would pool on the surface of that planet. And that's known as the habitable zone. So I mentioned that I'd worked for about 6 years with Lawrence Doyle, trying to get funding to provide a source of revenue for ourselves, but also for a small telescope up at Lick Observatory at the Crossley Dome to look for planets around the small eclipsing binary. And we got rejected every time. Some of the rejections were binary stars don't have planets. Some of the rejections were M stars don't have planets. And so even the experts who were reading our proposals really didn't know what was what. And in fact, most of what we thought we understood about planets, like much of physics and space, it may be partially right, but it's often wrong. But Kepler 16b, Aka Tatooine, was the first confirmed transiting circumbinary planet orbiting two stars. One of them is a small M star. And Lawrence is really a visionary. He's a fascinating man. He was the first I heard in a public forum to predict that we would actually learn about planetary atmospheres of alien worlds through transmission spectroscopy. And I'll talk a little bit about that later. But at the time, a very renowned scientist got up and said it'll never work. And of course it has. And indeed, within the first 6 circumbinary planetary systems that we'd found, in cases where you find a planet orbiting outside of 2 stars in a very tight orbit, Kepler 47c was discovered orbiting in the habitable zone of its star. And that's fascinating because we found many, many, many planets orbiting single stars before we found the first one that was in the habitable zone of its star, whereas it only took about 6 tries for a circumbinary system to be found where a planet was in the habitable zone. Now, Kepler 47c is not a habitable planet, but it might have a moon that could be habitable. And if you think about it, 3 out of every 2 stars you look up at the sky at are binary stars. Well, 1995 was the year that the first extrasolar planet was discovered orbiting a main sequence star that was recognized as such. But it was also the year, earlier that year, we had the XNEPS report, and we had the XNEPS workshop. This was exploration of neighboring planetary systems. And they worked out a roadmap of technology that would take us from detecting planets, learning about their orbits, to direct imaging, to spectroscopy, to learn what's in their atmospheres. A lot of people worked on this. They had a roadmap here of technology. You see they're doing radial velocity, astrometry, disks, direct imaging of Jupiters, more spectroscopy, detailed imaging. But where are transits? Transits are nowhere. At that time, transit photometry was controversial. And a lot of people in the field, very bright technical people, thought it could not be done. They didn't think that CCDs like this one. This is one of the CCDs that we used in the laboratory to demonstrate that CCD photometry can achieve the precision necessary to detect small Earth-sized planets. You need to achieve a precision of about 10 parts per million from the instrument noise perspective to be able to do that. Well, so I had more hair before planets, exoplanets. I have less hair here. I look a little bit more serious. That's probably because Bill is a real workhorse, and I'm working for Bill now. So I was thinking a lot about planets, and indeed, I was a skeptic at first too. People said, "What about star spots?" People had all kinds of questions, technical questions about what could possibly be the straw that breaks the camel's back. And one by one, we set up those dominoes and knocked them down. And after about a year, I was convinced that we could do this. And somewhat later, it took a little bit more effort to convince our colleagues and convince NASA that we were worthy of funding. So David Koch took the consolation prize in the '96 Discovery proposal cycle. We were not selected, but we did get $500,000 to use to do a hardware-based laboratory demonstration. So this is the laboratory setup that David Koch designed and that we built and then operated, and he led the whole effort. There's a telescope, there's an integrating sphere to illuminate a star plate here with holes for the stars. They get imaged onto CCD like this one. Actually, it was a Marconi, a little bit later device. And then Dave came up with this ingenious way to create transits. And as far as I know, it's the only way you can create Earth-sized transits in the laboratory in a robust, repeatable way. But you put a ribbon wire across a laser milled hole, and you put a couple milliamps through that, it expands by 1 atom, and that's enough to block 1 part in 10,000 of the light that's coming through that hole. And so down here are some of the light curves that we were able to obtain in the laboratory with this device, demonstrating the signal to noise that we could achieve against the instrumental noise for stars on the star plate in that setup. That, together with the discovery of 51 PEG, and then later, in 2000, of course, we discovered the first transiting extrasolar planet, HD 209458b. That was very important because at the time, there were still a lot of skeptics with respect to whether these extrasolar planets were actually planets. Perhaps, yes, they're substellar in mass, but perhaps they form much more like binary stars form than like planets form. And it took a while for theory to catch up and for us to have good ways to predict and model the voyage of giant planets as they transition and migrate from the outer solar system to the inner solar system. And a lot of them tend to break and stop in a 3-day period orbit. So I want to share some of the key science results from Kepler with you. I'm not going to be able to play all the greatest hits, but I'm going to try to hit some of them. So this speaks more to the impact that Kepler has had on the field of extrasolar planets. This is the first extrasolar planet. 1989 was the year this was discovered, but it wasn't recognized for some time to actually be a planet. There was a question as to whether it was a brown dwarf or what. But indeed, later on, that proved to be indeed the case, and that's due to Dave Latham. But if we look at all the planets that were discovered outside our solar system, not from Kepler, through 2012, then we have a whole bunch detected by radio velocity techniques where you look for the reflex velocity, kind of like a speed gun, to look for variation in the velocity of the star as it orbits the common barycenter. And that, by far, was the most successful method in terms of the bulk numbers and also reaching down reliably to small masses. These are the transiting planets that were discovered largely from the ground. And it's hard to detect an Earth-sized planet by transit or any other method. Earth covers 1 part in 10,000, a percent of the area of the sun. Jupiter covers 1%. You can achieve that easily using CCD in your backyard with amateur equipment today. So there were approximately 70 transiting planets that were discovered before Kepler flew. But you see they're still more or less moribund up here near Jupiter in terms of their size, and limited to a few days or so in orbital period. This one point here is Corot 7b, and that was actually obtained from the Corot spacecraft, which launched in 2007, or at the end of 2006. And then there's some microlensing planets. They have long periods because they're detected typically very far from their star, 2 AU or further. And we're starting to see some direct imaging. And you saw that direct imaging was called out on the roadmap by XNEPS. And so XNEPS got a lot of it right, but they got some of the details wrong, like we all do when we prognosticate. This is what Kepler has done to the field. So now we have, I think in this case this is about 3,400, but today we have over 4,000 candidates, 950 or so confirmed or validated planets. And you see we've really pushed the envelope down so that the bulk of our planets that we're discovering are smaller than Neptune. In fact, most of them are 2 Earth radii or smaller, thereabouts. And we don't have 2 Earth radius planets in our solar system. So these are completely different beasts from those that planetary scientists like myself grew to know and love through our voyages through the solar system on the planetary probes that NASA has launched, and ESA. And as we've accumulated data, we've pushed out the orbital period for which we can find such planets as small as Earth. So we're reaching out at this point to a couple of hundred days for the orbital period. Now that's not quite the Holy Grail, but we're on our way there, we believe. One of the biggest exciting news this year was the fact that we were able to use a statistical validation technique on all of the multiple planet systems we've discovered to actually dominate the field. So now we've detected and confirmed or validated more planets than anybody else, and most of ours are very small. Moreover, they're in multiple planet systems. These are very interesting. You want to know about the system, not just about a single planet around a single star. We want to know if our own solar system is normal, whether it's weird. In fact, it's a lot less weird than it used to be against the backdrop of exoplanets, but it's not normal either. So there's a lot more to learn. So this was a phenomenal step forward for the field and for Kepler. We have made progress in finding small, most likely rocky, possibly rocky planets. This is 62E and F, about 1.5 or so, 1.6 Earth radii. They could be rocky, and they're both either 62E is on the inner edge of the habitable zone, and 62F is smack dab in the middle of its habitable zone. Now this star is a little bit smaller and cooler than the sun, so the habitable zone, that green lane, is closer to its star than our habitable zone is. But at that distance, it receives about the same radiation that we do from the sun. Now I promised to talk about acoustic oscillations in stars because this is the unsung story of Kepler. Why do stars sing? Well, pay attention to this graph down here. So if you have a starquake, stars are big balls of fluid, and they resonate kind of like bowls of jello. And if you have a starquake, you can excite an acoustic wave, and it will travel down towards the center of the star, but it will refract back because of the sound speed change. And then it will bounce around, and if it comes back to the same point it started at, it keeps on going around. So you set up these quasi-harmonic oscillations. And just as with bells, the bigger the star is, the deeper the tone, right? The lower the frequency or the lower the pitch that it sings. So astronomers, astroseismologists, can study the intervals, the spacing of the different modes, and the center frequency, and learn about the mass, the age, and the size. In fact, for these stars, you can measure the age and, the mass and the size to a couple %, which is phenomenal because they're just point sources. We can't see them. This is how we've changed the field in astroseismology just with the first couple of years of data. This was published in 2011, but there are over 500 stars for which we've observed these P-mode oscillations or pressure mode oscillations, all up and down the HR diagram. Before Kepler, there were maybe a couple of dozen stars for which we could do this via Doppler techniques from the ground. And this is the sound that the stars are making. Now it's sped up so that we can actually perceive it because you don't want to be here for 4 years, do you? I don't. Now I want to highlight one of the weirdest discoveries, perhaps the most bizarre discovery Kepler has made, and that is that we saw this light curve early on where you see this hair. These are transit-like features occurring every 16 hours or so. Well, precisely every 16 point some hours. But they change depth, and planets don't do that. So this was reliably detected by our pipeline each and every time we ran it, but it was ignored because people were interested in planets. This looked like some kind of strange artifact. But Saul Rappaport saw this and said, this must be something interesting. What could possibly be going on here? And it turns out that this planet is so close to its star in the 16-hour orbit that it's evaporating. And so it's about 2,300 Kelvin on the surface, and it's evaporating material off the surface. It's blowing off. It's then cooling and condensing into a comet-like tail. So what we're seeing is the comet tail occluding or blocking the light from the star. And because the activity changes as a function of the radiation of the star, and the star has spots, so you get these outbursts, and it changes over time, then you get a changing depth of the transit-like feature because the tail is changing. Now we only have one other candidate in all of our 200,000 light curves that looks like it might be one of these. But these are very short-lived objects. This, we believe, will evaporate within 200 million years, which is kind of the blink of an eye in terms of the age of the universe. Well, I want to tell you where planets come from. They start out with raw data. So we have the postage stamps coming down from the spacecraft. And this essentially is my baby, and there are a lot of people here who have helped me over many years to build this thing. We have to do the standard kinds of corrections that photometrists do when they collect data from CCDs on the ground. We have to calibrate the pixels, remove on-chip artifacts. We have to then sum up all the pixels underneath the image of each star to count the counts, and that gives us the brightness as a function of time. You can see an example here. You also see some other things going on that are systematic due to how the instrument is drifting over time. So we have to identify those in this module and remove them so that the data are clean enough to present to our detection algorithm, which then combs through the data looking for transit-like features. And it does a really good job of finding transit-like features, and it turns out, I'll tell you later, that a lot of other things can look like transit-like features too. So it's very challenging. But then we hand it over to data validation, which then creates a suite of diagnostic tests that help the scientists and astronomers and astrophysicists decide whether this is a planet or not. It can help make or break that hypothesis. And then we leave it to the threshold crossing event review team, a group of people, scientists in the science office and on the science team, to actually decide what's what, planet or dead. This is an example of one of the end products from the Kepler pipeline. This is a data validation summary report where we summarize the most important information on one page. This is a really good looking signature of a planet transiting here. It's folded at the period of the planet. You can see the individual transits marked. You can see the full light curve. You can see the odd and even, and everything's black here. If anything were red, it would be called possibly into question, but everything is black. This was created on 30th of October 2012. This was the subject of a very important discovery announced earlier this year, Kepler 186f. This is the discovery shot. This was what gave the astronomers the information they needed to say this is a very interesting object and most likely a planet, barring any unforeseen circumstances that get turned up later by the follow-up observations. But this is what everybody wants to see when they're looking at these reports. Now, unfortunately, we've had a plague of planet-like signatures, and as we accumulated more data, it's kind of like bales of hay falling on your head and you're looking for golden needles. So the system was speeding up as we were accumulating data, and it was running faster and faster. And so it was difficult to deal with. In fact, it was so difficult, we had to change our architecture for our hardware. So these were our local clusters, our local computers we used for the first 3 or so years. And then it became apparent that we couldn't keep up with the data. Well, we could keep up with the data, but we couldn't go back and reprocess it to take advantage of all those improvements that we'd made to the software, having learned so much about the instrument and about the sky in the meantime. So we moved our operations to the supercomputer. Kepler is a story of many threads having to come together to enable it to fly when it flew and to be successful. We needed technology. We needed back-illuminated CCDs. We needed computers on board fast enough to collect the data and deal with it. We needed the political will of the astronomers in the community to get behind this project and believe that it could work, because it was not cheap. And we needed outstanding computational resources available here at NASA Ames to do this job. If you took all of the data validation reports from a typical run across 4 years of Kepler data, you would create a stack of paper 150 stories high. This is the Chicago Spire. I think that's only proposed. It hasn't been built, but that might be a little bit taller than this stack of paper. And I don't know anybody that would want to crawl through 150 stories of paper in order to decide whether something's a planet or not. It's really an overwhelming job. We'll come back to this point a little bit later. So in the end, having analyzed all the data from the pipeline and gone out and gotten additional information, additional observations, and done additional validation analyses, we have Kepler 186f, which is our first example of an Earth-sized planet in the habitable zone of a main sequence star burning hydrogen in its core. The Kepler 186 system. So it's orbiting an M star about half the mass and half the size of our own sun, so the habitable zone is much closer, but it's a little bit bigger than the Earth, but not too much. It receives a little bit less radiation than we do, but in principle, that's not a problem. Now, people have other issues with M stars because they flare. The habitable zone is so tight that most of the planets would be locked, like the moon is locked in its orbit about the Earth. I personally don't think that's a problem. Having studied Venus, if you want to know what the temperature of a particular place is in the Venus atmosphere, it's a function not of the angle to the sun, it's a function of your altitude and your latitude only. That's because the wind on Venus in the thick atmosphere circulates the heat so effectively from the sun side to the anti-sun side that it doesn't matter whether it's light or dark. So you just need a thick atmosphere. Hopefully not too thick. Now, we have collected a number of small habitable zone candidates, and this is the latest and greatest I got from Natalie. Thank you. And we have a lot more candidates, and some of these have been confirmed or validated. And these green lanes indicate where we believe the habitable zone is. Now, there are 2 marked here because we're not quite certain as scientists what we should define to be the habitable zone. There's some controversy, and I'll say there's an active discussion and dialogue going on. But this, on the x-axis, is the flux received by the planet relative to what we receive here on Earth. So one is where the Earth is way up here. This is the temperature of the star. So this allows us to conveniently plot all of these points on one graph and see where they lie. This is very exciting. This is what we hope to see when we launch Kepler. Are we there yet? Well, the answer is no. We need to understand what the discoveries we've made mean. It's no time to fall asleep. We need to keep pressing on, and fortunately, headquarters has allowed us to go on for an extended mission, a closeout mission now, to finish the job that we started, namely to define and determine the frequency of Earth-sized planets in the habitable zone of sun-like stars in our target sample, which then informs us about the galaxy. In fact, Natalie is the chief scientist, our mission scientist, who's been thinking about this, and she's been putting together the recipe for how we're going to bake this cake. So we need to have the best planet candidates and set of confirmed and validated planets that we can. And that's where the SOC comes in. That's our job, is to find the planet signatures in the data. We also need to characterize the completeness of the Kepler planet discovery system. It's not enough to know that you have a bunch of pretty shiny marbles. You want to know how many you missed. If you want to know how many are in the bag that you still have that you can't look in directly, right? You also want to know how many of those marbles are false positives. So you need to understand the reliability of your sample in order to draw the conclusions you want to draw. You need to know about the stars. In fact, we could not afford to know as much about the stars when we launched as we really needed to in order to do this job. So we're playing catch up after the fact because we could simply not afford to do this for, what was it, Natalie, 5 million stars in our catalog, something like that? Thank you, Bill. 15 million stars. That would have taken a long time, at least with assets then, and probably still today. We also need to know about the background eclipsing binary distribution, because that eclipsing binaries, as I've said many times before, for exoplanets are the scourge of the universe. They mimic planetary transits, and they're great when you have circumbinary systems, but otherwise, who cares? Well, actually, we have people on the science team that care a lot, and it's really cool science they're doing. Furthermore, we need to understand what kinds of stars we chose to be our targets. We were very selective. So there are selection biases in the pool of planetary targets, of stars, that we chose to observe. We need to know how the properties of the stars we chose to observe relate to the properties of the general star that we find in the solar neighborhood. And then we can tie it all together and understand what's going on. Well, we've made some initial attempts. In fact, the community has made initial attempts to identify what the occurrence rates are for small planets, and you see 2 published results here. This is a recent preliminary result within the Kepler team itself by Chris Burke, who works in the science office, and he estimates, based on our understanding of our pipeline completeness and reliability, that about 1/3 of the stars that are main sequence stars in our sample have planets between 1 and 2 Earth radii with orbital periods between 50 and 200 days. Now that's a very exciting piece of real estate. We want to improve that. However, it depends on what assumptions you make about your system. And so Chris has done due diligence and found that depending on what assumptions he makes about our stars and about what we're doing, he can get an answer anywhere between about 0.2 and 0.6. And with tails that go up to 0.9 or so, and of course, tails that go down to about 0.1. I don't know about you, but at this point, I don't think that we have a result that we can be proud of that can actually carry us forward to understand what we need to know in order to support follow-on missions. So how do we characterize the Kepler planet discovery system? Well, it's a real sausage maker. First, we take the target star pixels, these postage stamps, we grind them through the pipeline to make light curves, identify transiting threshold crossing events. These are transit-like features, and those in the DV diagnostics go to the threshold crossing event review team, a group of people, so we have a people pipeline, that then pump out the planets. But we need to understand and characterize the completeness and reliability. So we've closed the loop by adding the capability within the SOC and the science office to inject artificial transits and background eclipsing binaries into the data. That provides the ground truth so that we can put those in and see how they all fall out. Do we detect the things we know we should be detecting? Do we make the right decision? Is this an eclipsing binary or is this a planet? So we can test our system, and we can test the people too. Now, in the end, I think it's too hard for people to do all that, at least in a complete, reliable, and consistent manner. So I've been working with some colleagues in the SOC and science office. Sean McAuliffe is here? Yes, there he is, okay. And Joe Catanzarite and Chris Burke. and Jeff Coughlin to build an auto-vetting machine based on using machine learning approaches to try to decide whether something should warrant additional attention or not. And we've been using a random forest approach. This is because we get about 20,000 threshold crossing events out of a typical run. Almost all of those are duds. Why ask a human being to sort through all that junk? What we want to do is train a machine based on what the humans have done in the past to do this job at least as well as humans, and perhaps even better. Because humans are fickle people. Your decision depends on whether you just had a cup of coffee, did you have a fight with your spouse, how much sleep did you get last night, is this the 10th or the 100th one that you're looking at today? A machine doesn't fall into those foibles. A human judgment is a wonderful thing, but it is, by its nature, flexible and changeable over time. So I don't have time to go into details, but what we've done recently is been able to then take this random forest, which is a collection of decision trees, say 1,000. Each decision tree then casts a vote as to whether it thinks an object based on the attributes, the diagnostics from the DV report, whether it should be a planet, an astrophysical false positive like a background eclipsing binary, or whether it's just an artifact of some sort. And if you then take the vote fraction for the vote for dud and the vote fraction for the vote for planet, and each candidate signature then is a point on this graph, right? Because everything sums to 1. If you're down here, you're a dud on the left. If you're over here, you're an astrophysical false positive. Now what I'm showing here, though, is that we can now color each point and attribute a posterior probability that it is a planet, that it is an astrophysical false positive, or that it's a dud. So now we don't just have a thumbs up or a thumbs down, we have a reliability estimate. Is this 80% significant in terms of should we count this as 80% of a planet or 0.01% of a planet? So this will help us with the statistics that we need in order to finish the job. So at this point, I'm going to turn to the bridge between Kepler and TESS, and that is, everybody knows, take off your hats, that Kepler died in May of 2012 when we lost our second reaction wheel. And there was a lot of moaning over that. We were all crushed. It had been a long, good ride, but we were hoping for another 2 to 4 years. But yay, verily, the Ball Aerospace Technical Services Corporation came up with a great idea for how to resurrect Kepler, and the community came up with great ideas of what we should do with this mission. We're dubbing it K2, and it was approved by the Singer Review earlier this year. Kepler's gone through some changes over the years. So at first, when we launched it had 4 reaction wheels, and it thought itself to be a go-kart. Then in June of 2012, we lost one of our reaction wheels, and it became a tricycle. And tricycles are a little more stable than go-karts. And in fact, our pointing behavior was a little bit better with 3 wheels than it was with 4. We launched with 4 wheels. 2 of them turned out to not be so good. They started misbehaving shortly after launch. We didn't recognize that until the first one failed. And we went back and dug into the engineering data. But then last May, we lost the second fickle wheel, and we're a bicycle now. But bicycles are great. So we're actually conducting observations now with K2. This is our first light image in the ecliptic, and we've chosen fields around the ecliptic or the orbital plane in order to carry out this mission. The way it works is that with the Kepler spacecraft, we can use the reaction wheels to point anywhere on the sky we want. What we can't do is use reaction wheels to control the roll. But if that's the sun, and this is the orbit, as long as I've got the sun on the midline of the solar rays, it's roughly symmetrical and it wants to stay there. And so we only have to actuate the thrusters once in a while to bring it back to point. Kind of like a rowboat in a stream, tied to a tether, right? It wants to line up with the stream. So if we point it this way, as it's orbiting around the sun stays on the midline, and we can stay pointed at that emergency exit, which is very important for everybody to know where it is, for as long as 80 days before we have to find another emergency exit. So we do that 4 times a year. And we believe that we have enough fuel on board to continue this mission for another 2.5 years or so. So that's a very exciting mission. It's also going to pave the way to TESS, which is the next one, because it's going to be looking in fields looking for planets that are similar to those that TESS is going to be looking for. So we were very elated a year ago or so when we heard that NASA had selected TESS for the Explorer program to launch in 2017 to look for the nearest and best exoplanets to follow up and characterize for the next 50 years or so. While it does this, following on the success of Kepler. Kepler looks at a field of view about the size of the palm of your hand, held at arm's length. It's a light cone about 3,000 light years deep and that wide. But there are 400 fields around the sky that you could point Kepler at when it had 3 or more reaction wheels. But TESS focuses its attention on the nearest 200 light years, and it's an all-sky survey. And the way that works, because we can't observe all the sky at once, is that it observes it in 26 different chunks. So it's 4 telescopes, each of which has a 24 by 24 degree field of view stacked one on top of the other. So it's 24 by 96 degrees high. And you go from the equator a little bit over the pole. And so you cover one of these swaths, if you can just barely see them, like that. And of course, we're always covering this spot here while we're operating in the northern hemisphere. We get a continuous year of coverage on 500 square degrees, which is 5 times the size of the Kepler field of view. Most stars are going to be observed only for 1 month, 27 days. So we're looking for short period planets, but we're looking for super-Earths and Earths. And those are actually very exciting because those are the kinds of planets that James Webb and other assets in the near future will be able to follow up and characterize so that we can learn more about their atmospheres and what makes them tick. TESS is a small spacecraft and instrument with a very large appetite. This is a very happy proposal manager with one of our cameras, right? Now, this man and this instrument could fit in the barrel of the telescope of Kepler quite easily, just to give you some size reference there. And this is a mock-up, a full-scale replica of the TESS concept spacecraft and instrument, although you can't see the cameras in there. With George Ricker, Sarah Seeger, Professor Sarah Seeger, Josh Wynn, and Roland Vandersbach, our deputy principal investigator, and George is our principal investigator. They're all at MIT. If you look at the science team for Kepler and for TESS, you'll find that there's a strong overlap. There's a huge interest in TESS. There's a huge interest in K2, and all of it has come about because of the success of Kepler. TESS will identify the best and smallest exoplanet targets because it's looking at stars that are 100 times brighter. So you have 100 times as many photons to work with to get spectra as you do with the typical Kepler target. We'll be able to get masses because almost all of them will be subjected to radial velocity. We can reach them with radial velocity. With Kepler, we can only get masses for a small fraction of the planets. Those are the most exciting finds we have because once you have the mass and the size, you can estimate the density and then start arguing over what it's made of. And we'll be identifying these planets and following them up with James Webb Space Telescope, extremely large telescopes, probes, and other large missions. And eventually, what we hope to do is to do transmission spectroscopy in transit by taking a spectrum out of transit and taking one in and noting that a small fraction of the photons from the star pass through the atmosphere on their way to the telescope so that we can actually analyze the spectrum and look for species associated with life. We want to look for ozone and oxygen, water vapor, methane, CO2. Plants love carbon dioxide. If you have carbon dioxide and water, and then you might have plants. And as Bill Berkey said this morning, if you have plants and you have water, you might have flying fish because you can have oxygen for the flying fish to breathe. So this is something that I hope I see in my own lifetime. I had no idea 20 years ago when I started working on this that we would be so successful or that I'd be standing here today talking about the phenomenal successes of Kepler. And it's the product of many years of effort on thousands of individuals' part. And a lot of it has taken place here in a very magical place, NASA Ames Research Center. It's just a hotbed of enthusiasm, innovation, and in all aspects for space science. So here's my summary. Kepler has returned a bonanza of planets, far more than any other mission or project, but far more importantly, they're much more interesting in terms of leading us down the road to find evidence for life. The first step is to define the frequency of planets and where you find them. We do have about 3.5 years to go where we need to characterize the completeness and reliability of the Kepler mission. Machine learning, I think, is going to really take over because it really is the only thing practical to do the job in a consistent and thorough fashion, and it's testable. Humans are not testable, not in this kind of context. And other missions like TESS and Plato, a European mission that might fly in 2024 that was just selected for launch last year, or earlier this year, excuse me, are going to look at a much larger real estate on the sky, and they'll need machine learning techniques. astronomers are being dragged kicking and screaming to the big data era, where instead of focusing our own eyes and our own hands on a piece of data, we need to train machines to help us do that job. K2 is very exciting. It's gotten underway, and it should bridge the gap between Kepler and TESS and train a lot of the people who are going to be doing follow-up observations for TESS on very similar objects. And with TESS, every month you get a slug of data and you get a slew of planets to follow up. So they're going to have to keep pace. And we hope, crossing our fingers, that TESS will fly in August of 2017 and start mapping the Earth and super-Earth-sized planets across the sky. So how am I doing on time? All right. I'm going to come back to this. So for those of you sonophiles, this is one of my favorite objects. It's an eclipsing binary. This is time in days. This is the change in intensity, and this is an eclipsing binary. But you see that there's something wrong with the printer here because there are all these smears here. And if you focus in, you see they're high-frequency oscillations. So this is a pair of stars, at least one of which has high-frequency pulsations going on. I don't know what the physical mechanism is. That's what our asteroseismologists are for. And this is the Fourier domain, so this is a periodogram. But it sounds really cool, so I'm going to play it for you. Oh, let's see. Well, let's try this one. Let's try this. So the base thumping is really the eclipses, so that's not thermomechanical energy. But the whistling is stuff going on inside the envelope of the star. And this is a very interesting star because we thought for half a second this might be a black hole. And if so, it would have been a phenomenal discovery. But reason took over after half a second. And this is what we've done as a heartbeat star. And I'll explain what's going on here. So here's the light curve. This is time in days. And it's 42 days in between each of these spikes. And what's happening is we have two A stars that are nearly identical, and they're in a highly elliptic orbit, and they're broadside. They actually don't eclipse each other. But when they get close together, they perturb each other gravitationally, and they radiate energy off each other, and they change their shapes so that you get a big spike every 42 days, and you have all these overtones that are being excited. I think the 91st overtone is the one that's dominant if you look in the Fourier domain. And so you end up with this highly periodic structure on top of a fundamental at 42 days. And this is a new class of binaries that has been elucidated by Kepler, and they also sound really cool. So with that, I'd like to open the floor for questions if anybody has any.
Can you hear me? Good. Is this thing on? So if I go back to your plot of A to Earth distributions, yeah, that's the one. Are you comfortable, confident saying that the values near zero are ruled out? Because none of those plots goes down to zero, and I think if it's true that zero is, or effectively zero is ruled out, that's a very exciting result.
I personally do think it's ruled out. These other analyses are either making reasonable but somewhat ad hoc and wrong assumptions about the completeness or reliability of the sample. And one is basically a pipeline that was built by a graduate student that's just not quite as sensitive as ours is, and he even acknowledges it's a very preliminary result. Natalie would remind you, and Bill Barucki reminded folks this morning, that we have yet to discover an Earth-sized planet in the habitable zone of a sun analog star. That's still the holy grail that we're still pursuing in the data. And so in some sense, these results are extrapolations, but we've got a larger sample ourselves now And what we're doing is trying to understand the sensitivity of the outcome of the analysis based on the extremes of our knowledge of what's going into the calculations and what's happening on the sky and in our instrument. So, but I'm comfortable with right now, a third of stars that you look at that are burning hydrogen have a 1 to 2 Earth radius planet. I think that's the best bet we have. And in the end, I think we're going to have a very good result.
Hi. Based on what you've seen so far, what would you say is a typical stellar planetary system, and how would it be different from ours?
Well, it's kind of like going to the zoo. So what's a typical animal at the zoo look like? I'm not sure if I can point to just one animal and say, that's what you see when you go to the zoo. However, we have an enormous number of these very compact multi-planet systems. And those seem to be, in some sense, because we see so many of them, that seems to be a very predominant hierarchy of, or topology for us to find these planetary systems in. So keep in mind, Kepler 11, which was the poster child for multiple planet systems, discovered fairly early in Kepler's mission, had 6 planets, the 5 innermost of which are within the orbit of Mercury, in terms of their distance from their star, the outer of which is within the orbit of Venus. So nature seems to have a predisposition to forming planetary systems that are highly coplanar and that are much more dynamically packed than our own system. And so we believe that these systems actually didn't start out that way. We believe they evolved. But we look at our own solar system, we think, oh, it's been like this for a long time. Our own solar system has evolved too. But the degree to which these systems have evolved is very marked. And indeed, the first planets we found were these hot Jupiters, which must have migrated in from the outside and could not have formed at 0.04 AU from their star, right? So change seems to be the rule, and we're trying to assemble enough examples so that we can start teasing out the rules lying underneath what we see in nature.
So please join me in thanking Dr. Jon Jenkins. I see that we do have one more question, so let's go ahead and put that in there.
I'm just curious to know what is the legal implications of all these discoveries. Can the U.S. claim the land of all these planets?
I'll have to turn that over to one of our bosses, Michael McKay here. Perhaps he could answer that question. Well, I'm no expert, but I believe the Space Act Treaty prohibits us from claiming land as our own, at least on other planets in our solar system. I would see no reason why that would not pertain to other planets. But of course, by the International Astronomical Union's definition of planet, none of these are planets anyway.
Okay, on that note, thank you again.